Welcome back to linear algebra. In this video, we are going to be working with isomorphisms. As I hinted previously, the value of isomorphisms is that you can find a way to translate a linear transformation on one vector space into a linear transformation on an isomorphic vector space. The goal there being taking something that you are familiar and comfortable with working with and using that instead of a more unique, unfamiliar space and properties. So without further ado, let me get my head out of the way and let's dive in. Here is some word soup for you. Let V be an m-dimensional vector space. Let W be an n-dimensional vector space, and let T be a linear transformation from V to W. Doesn't have to be one-to-one or onto. We are not specifically looking at an isomorphism here. So for any linear transformation T, there is a matrix transformation A, which maps from Rm to Rn, which is isomorphic to T. Talking about a transformation as being isomorphic is a little bit strange at first glance. And this is one of the places where I think a picture is worth 1,000 words. So I'm going to draw a strange little sketch here. I'm going to draw kind of a box with the corners labeled as Rm, Rn, V, and W. And of course, my transformation T maps from V to W. And I've said that I want a transformation A, which maps from Rm to Rn. So let's go ahead and label that and call it A. Remember that V is an m-dimensional vector space. And we showed that any m-dimensional vector space is isomorphic to Rm. Likewise, any n-dimensional vector space, such as W, is isomorphic to Rn. And here I have put double-headed arrows to represent the isomorphisms, because linear transformation T and matrix transformation A may or may not have inverses. It's always possible that we are losing information by doing this. But for an isomorphism, that's not the case. You can go from V to Rm, you can go from Rm back to V. So if we know what T is, we can start with a vector in Rm. We can use the isomorphism to turn it into a vector in V. We can use transformation T to turn that into a vector in W. And we can use the other isomorphism to turn that into a vector in Rn. That's the proof of the theorem, entirely by picture. Starting with a vector in Rm, there is a way to translate that into a vector in Rn. And a matrix transformation is defined entirely by its action on the basis vectors. So if we take each of the basis vectors in Rm, turn them into vectors in V using the isomorphism, evaluate T on each of those vectors, and then turn those into vectors in Rn, again using an isomorphism, we will establish everything we need to develop this matrix transformation. All right, that's all well and good, but before I get the picture out of the way, the one thing that I want to mention here is that this is completely backwards of how we will ever use this thing. The use of this sort of contrived machinery is to take a vector that is in V, use the isomorphism to turn it into a vector in Rm. The nice thing about vectors in Rm is there is some really fantastic computer software to apply matrix transformations to those, turning it into a vector in Rn. Then from there, because we have an isomorphism, we can get back to W. It's the long way of getting there. But the advantage is that when you're dealing with Rm and Rn, you can rely on computer software that is already very well established. And there are a lot of places where we actually do this. So as a quick example, let's take a look at a transformation we used in a previous video. Let's think about the transformation going from P3 to R2. The evaluation T of f of x is the vector f of 1, f of 2. We saw when we looked at that the transformation on the basis vectors, T of 1 is 1, 1, T of x is 1, 2, T of x squared is 1, 4, and T of x cubed is 1, 8. So if we want to take a vector in P3, a0 plus a1x plus a2x squared plus a3x cubed. The simplest isomorphism takes the coefficients and turns them into Euclidean vectors, or the components of a Euclidean vector. I forgot some words there. You can show for yourself that this is an isomorphism between P3 and R2. So we can rewrite this transformation by saying that A, acting on 1, 0, 0, 0, needs to map to 1, 1. And that A acting on 0, 1, 0, 0 needs to map to 1, 2. A acting on 0, 0, 1, 0 needs to map to 1, 4. And A acting on 0, 0, 0, 1 needs to map to 1, 8. And as we've seen before, given the action on the basis of a linear transformation between Euclidean vectors, we can write the matrix. It's just going to take these results as its columns. A is going to be the matrix 1, 1, 1, 2, 1, 4, 1, 8. Now, using this trick, if we have a random polynomial, I don't remember the polynomial that we evaluated this on in the previous video, but let's determine that f of x is 3x cubed minus 5x squared plus 4x minus 9. We can translate that into the Euclidean vector 3, I'm sorry, I'm doing this backwards. -9, 4, -5, 3. Constant, coefficient on x, coefficient on x squared, coefficient on x cubed. That's the way we set up the isomorphism to give us what we are working on. Now, to evaluate t on f of x, that's the same thing as multiplying my matrix times my vector. And if you multiply first row times column, it's -9 and 4, which is -5, and -5, which is -10, and 3, which is -7. We've got -9 and 8, which is -1, and 20, which is -19. I'm sorry, we had -1, then we got -20, which is -21. And then let's see, 8 times 3 is 24, -21 plus 24 is 3. You can try using the direct evaluation. F of 1 is -7, f of 2 is 3, checks out. Just another way of approaching something. Before I go on to one more example here, I do want to stress what we just did is absolutely the hard way of looking at this problem. That's not the point. This particular transformation is a fairly straightforward one. But the advantage even then can come out if we don't have to do this just once or twice, but dozens or hundreds of times. And especially if the transformation that we're looking at becomes more complicated. If you program a computer to do this, inputting vectors into computer software is a lot easier than inputting other things. Just writing the software to parse a polynomial to use as input is exceptionally difficult. So this kind of a transformation really can make computational work with vectors and with the abstract vector spaces significantly easier. So with that in mind, let's take a look at one more example. Let's look at the linear transformation D. I'm going to take the version that maps from P4 to P3, and we're going to assign this as differentiation on the vectors, on the polynomials. So, in order to work with this, we need to know what differentiation does to the basis vectors in P4. The basis vectors on P4 are 1, x, x squared. Why am I putting a lowercase d? I have to find this as a capital D. Anyway, 1x, x squared, x cubed, and x to the fourth. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. And the derivative of x to the fourth is 4x cubed. Now, we know that the canonical isomorphisms are going to map a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth as the vector in R5, a0, a1, a2, a3, a4, and in P3, b0 plus b1x plus b2x squared plus b3x cubed is the same thing as b0, b1, b2, b3. So with that, we should be able to establish a matrix to represent differentiation of a polynomial. Just translating left-hand and right-hand side of each of these basis vectors into their Euclidean isomorphisms. So 1 is 1, 0, 0, 0, 0. And you're going to get out 0, 0, 0, 0. X is 0, 1, 0, 0, 0. And 1 is 1, 0, 0, 0. X squared is 0, 0, 1, 0, 0. And in P3, 2x is 0, 2, 0, 0. X cubed in P4 is 0, 0, 0, 1, 0. And 3x squared in P3 is 0, 0, 3, 0. Finally, x to the fourth in P4 is 0, 0, 0, 0, 1. And 4x cubed in P3 is 0, 0, 0, 4. So once we have made that translation, we can write the matrix transformation by taking its columns as each of these. Giving us a result that looks something kind of like that. And so, once again, fairly innocuous here, because if I wanted to take the derivative of a polynomial, say x to the fourth minus 3x plus 2, I would just differentiate. Get 4x minus 3. But I could also take x to the fourth minus 3x squared plus 2 and turn that into the column vector, which is going to be 2, negative 3, 0x squared, 0x cubed, 1x to the fourth. And I can multiply that by matrix A here. And first row times that column is going to give me -3. Second row times that column is going to give me 0 and 0 and 4. And if you take this column vector and translate it into a polynomial, you get -3 plus 4x cubed. So that's the basic idea of using isomorphisms between arbitrary vector spaces and Rn in order to write matrix or linear transformations on abstract vector spaces using matrices. Now think about the applications there. We have spent a lot of time solving matrix equations. If we have an equation involving a linear transformation in other vector spaces, we can translate it into a matrix equation or a vector equation in Euclidean vectors. We can use all the tools that we've been looking at so far in order to solve it, and then we can translate back to get our answer. This is an incredibly powerful tool in numerical differential equations, turning differential operators into linear operators, translating that into matrices, putting it into a computer and having the computer solve for you. This is a powerful tool in working with, excuse me, this is a powerful tool in working with really anything that you can find to turn into a vector. You can also use this process to look at eigenvalue problems for abstract vector spaces. You can use this process to diagonalize an abstract linear transformation. You can use this process to describe the orthonormal basis of an abstract vector space. You can use this process to find the orthogonal diagonalization and all of the benefits that we talked about with that. All of those tasks are beyond the scope of this course. If you continue on in a pursuit of mathematics, you may go on to take an advanced linear algebra course, which addresses some of those things. You may also go on to study functional analysis, which takes all of these tools that we've talked about here for finite dimensional vector spaces and allows you to use them for infinite dimensional vector spaces. If you're going on to study physics or many of the engineering disciplines, you will also encounter functional analysis. It is the foundation of quantum mechanics, although that will take it another step further and ask you to do functional analysis on complex numbers instead of real numbers. Just a couple of different ways you can build on the skills we've talked about in this course as you move forward and look at some other things. That's all I have for you in this video. That's actually all I have for you in this course. Take a look at the practice problems, see where you're coming along with that, and I hope to see you in another course.